So our first question on Ask Mr. G comes from our streams at the beginning of the week last week of what would happen if the moon blew up? Well, we could ask Sir Isaac Newton what would happen if the moon blew up, and he would say that you need an outside force to do that. And there's two forces we could use. We could either use a direct collision to blow up the moon, or we could use Earth's gravity. The first option, probably the most basic answer, is it would make lots of large chunks, most of which would end up crashing into the Earth and destroying all life as we know it. So if we do option one, we'll never be able to see what would happen if the moon blew up. The second option, if we used Earth's gravity and do it gently and kind of, instead of blowing the moon up directly, sort of shred it apart, we would actually be able to see the effect there, all right? And so we're going to use Earth's gravity to go forward in this question. In order to do that, what the Roche limit is of two bodies in a system, okay? Roche limit is the term that we use for when an object's tidal force, its gravity, its gravitational attraction, is stronger than the cohesion of another object. So in this case, the attraction of the Earth being much stronger than the moon, and then all the parts of the moon getting pulled apart. There's a mathematical equation for this. It is 2.4 times the radius of the Earth, that multiplied by the density of the Earth divided by the density of the moon to the power of 1/3. Radius of the Earth, for all intents and purposes here, just simplifying it a little bit, is 6,378 kilometers. The density of the Earth, simplifying it a little bit, 5.5 grams per cubic centimeter, and density of the moon is 2.5 grams per cubic centimeter. If you plug all of these values in over into the formula, you'll eventually get to this step right here, 2.4 times 6,378 times 2.2 to the third power. How do you eliminate or reduce an exponent that's a fraction? The best way to do so, using a cube root. So we cube root of 2.2, and with that comes 1.3. Reduce all that, and it's about 19,900 kilometers. So at 19,000, almost 20,000 kilometers, the Roche limit is here at about 20,000 kilometers. Satellite orbit, 42,000 kilometers. And then the moon, it's all the way out at 363,000 kilometers, way beyond the Roche limit. Could we make the Roche limit larger? Could we increase it? If we want to increase it, then we have to use the same formula, but instead of trying to solve for the limit, 100,000 kilometers, instead of 363 for the moon. And to make that larger, if we keep everything else the same, we keep the moon itself the same, we keep the radius of the Earth the same, what would its density need to be? So you can find the density of this new Earth to make a Roche limit that is larger in radius than the moon's orbit. Why would we want to find the density? Because then it could tell us the mass of this new planet. We'll do that later. We'll divide both sides by 15,307. Reduce that fraction to 23.78 equals the density of this new Earth divided by 2.5, and that's to the power of 1/3. Now we're stuck again with this fraction exponent. But to cancel it out, just do a cube root. Whatever you do to one side, you gotta do the other. It gives us a density of this new planet, this new Earth, of around 7.2 grams per cubic centimeter, which is about the density of the element chromium. How can we get an Earth that is roughly the density of the metal chromium? Well, we need a lot of extra mass, and that means a lot of extra mass with large numbers. And in science, we use something called scientific notation to help us deal with really large numbers. In scientific notation, we use powers of 10. 1 times 10 to the 0 power. Well, 10 to 0 is 1, 1 times 1 is 1. Another way of writing the number 10, you could do 1 times 10 to the first power, because 10 once is 10, and 1 times 10 is 10. But then you could do 10 to the second power to do 100. 10 times 10 is 100, 100 times 1. So we could write 1,000 as 1 times 10 to the third. So in scientific notation, when we do 10 to the power, we mean that's how many zeros. Or you could also think of it as how many decimal places you move from the number 1, because 1 would be really 1.0. We're moving it 1, 2, 3 times, and you can add in the zeros there when you move the decimal place. There, if you use a negative exponent, you go the opposite direction. So instead of to the right, power of 10 in scientific notation, we go to the left. So if this is 1.0, we just go once over to the left. Now this becomes 0.1, 1/10. 10 times negative 2, we're just going the opposite direction, it's 1/100th. And then 1,000th, what we just did over there for the positive, 1 times 10 to the negative 3, move the decimal place 3 times to the left for 1, you get 0.001. 3 zeros. Just understanding scientific notation, because we're talking about volume of the Earth, and that's 1 trillion cubic kilometers. What's 1 trillion? 1 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. There's an easier way to deal with this math, and that's just doing 1.0 times 10 to the 12 cubic kilometers. That's the volume of the Earth. And then the mass of the Earth is, we also can use scientific notation, 5.97 times 10 to the 24th power. Moving this decimal place over 24 times to the right, and that means you're including 22 zeros after the 7. Incredibly large, incredibly massive object. And so we can actually calculate the actual density of the Earth. Instead of just using that rough approximation of 5.5 grams per cubic centimeter, we can actually do it in kilograms per cubic kilometer. When you divide by powers of 10, you subtract 24 and 12. We're doing division. 24 minus 12, that's 12. So our answer is going to be 5.97 divided by 1. So that's the actual density of the Earth, using a rough approximation for volume in terms of kilograms per cubic kilometer. Because the Earth is so large, we'll use larger units. So we are going to take the density we want, place it into the d equals m over v equation, and we're going to take the volume that we already have from previous 1 trillion cubic kilometers, and we're going to find this new mass that we need. We're going to multiply both sides by 1 times 10 to the 12, 1 times 10 to the 12, and when you multiply powers of 10, instead of subtraction, you're going to add them together. Current mass, however, like we've said before, we used in the beginning, kind of similar to the density, 5.97 times 10 to the 24 kilograms. We are going to need an increase of 1.23 times 10 to the 24 kilograms. Where can we find this extra mass? We have our solar system. I'm just going to look at the inner solar system plus the next planet, Jupiter. We have our sun. The next planet out, we have Mercury. Then larger, Venus. And similar in size, Earth. Smaller than Earth, we have Mars. And in between Mars and the largest planet in our solar system, Jupiter, we have this area called the asteroid belt. The location where we have been potato-shaped rocks to the size of a car to the size of a dwarf planet. The only one, Ceres. Ceres is the largest asteroid, but it is spherical under its own gravity, and therefore has been considered now a dwarf planet. It has a mass of 8.96 times 10 to the 20 kilograms, which makes it about 30% of the mass in the asteroid belt. It takes up a third of the mass in that area, that region of our solar system. So 8.96 times 10 to the 20. We can work this over to 10 to the 24. So we want to work to the left and add to our power of 10. So we work over here. That's once. So now it's 10 to the 21st. It would be 0.896 times 10 to the 21st kilograms. Well, we want to get to 24. So we add decimal place one over more to the left and we fill in the blank with a 0. So now it's 10. So we add the decimal place further over to the left. Add another 0 in the blank. Now it's 10 to the 23. And we need one more order of magnitude, so we move over to the left, one more, fill in the blank, add that 0 to the left of our decimal place, and now it's 10 to the 24. We are looking at, if you could mine the entire dwarf planet of Ceres and bring it to the Earth, we would need 1,373 Cereses. Well, the problem is, Ceres alone, one of them takes up 30% of the mass of the asteroid belt. So we have some problems. The first problem is we used a Roche limit based on the Earth and Moon system. So we're trying to destroy part of what helps us determine the Roche limit of the center of gravity between these two objects. That's going to cause some inaccuracy in our answer. Also, density is a ratio. That's also an issue, because as we're adding more and more mass to the Earth, and making it have higher amount of gravity, we're also increasing its volume too. And so we would actually need much, much more matter than is available in the solar system. But if you could though, what would actually happen? The moon would be inside the Earth's Roche limit, now at 364,000 kilometers. The moon, as it's moving and orbiting in its counterclockwise revolution around the Earth, would start being pulled away and shredded apart and leaving a trail and outlining its revolution in bits of moon. And so what would eventually happen is you would end up with a ring system larger than Saturn's, but also slightly duller, because the moon is about 3% volume water, whereas Saturn's rings are about 99% water, ice. And so ice is more reflective than the regolith and rock of the moon. It would be a little duller, but still visible from the Earth and from the other planets, because there's no longer a large body stabilizing the Earth like a top rotating on its axis, you would no longer have a stable 23.5-degree tilt. Instead, it would wobble back and forth, which is going to throw the seasons out of whack, which would also affect other biological systems on the planet. Take Mars, for example, which currently has a 25-degree tilt. Without a large moon, it has 2 tiny moons that were captured asteroids. Its tilt has varied between 13 and 40 degrees over the last 20 million, or 2 times 10 to the 6 years. Also, our tides would now be solar-based and always happen at specific times. High tide at noon, high tide again at midnight, and then low tides at 6s. So they'd always be at the same time, but they would be much, much weaker because you no longer have the moon's gravity pulling. The ring system wouldn't be enough to stabilize the axial tilt and wouldn't be enough to influence the tides because they would be distributed evenly in all directions around the planet's equator. So that's what would happen if we could make the Roche limit increase in size and slowly shred the moon. But more likely, the moon is moving away at 3 centimeters a year. And so either the moon would end up locked in a faraway orbit. It would take 47 days to revolve around the Earth, or it would eventually just leave altogether. You would end up with a wild season and wild axial tilt with a solar-based tide in 50 billion years. So the same result without the pretty ring system. However, the sun is going to become a red giant in 5 billion years. And then everything within inside Jupiter's orbit is going to be destroyed anyway. But it was pretty cool to think about.